Hello, we will now talk about Barron's topic 7.8, which deal with probability. Pretty much this is like 1/4 of the material of the course. So this is going to be a really quick run through, of the major topics, but, there's no way I can explain everything in depthly. So what, the hope is that you will study this stuff and you'll look at it more completely and then ask me questions about what you're having difficulty with. Anyway, so like I said, this is going to be a kind of a quick run through of some major topics in probability. So the first concept is the law of large numbers. The law of large numbers, it states that the more trials there are, the larger your sample size is, the closer the estimate, in other words, the statistic, will be to the parameter, to the true value. And there's different ways of wording this. And so that's like the true population value, we will say. There's different ways of wording this, but just in general, the law of large numbers says the more you increase your sample size, your number of trials, the closer your value is going to be to the actual true value. All right, so we have some formulas you have to know, and a couple of them are on the formula sheet. All right. So the first one is the generalized addition rule. So the generalized addition rule, so if you look on page 1 of your formula sheets, here's our probability formulas down here. And this is what is known as the generalized addition rule. That union symbol, A union B, that means the probability of A or B. And so the word or in math means add. It means the probability of A plus the probability of B, but you have to subtract off any overlap there is. That little symbol there means intersection. So that means A and B. So that is the generalized addition rule, is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay. The conditional probability formula is the next formula there. So that little vertical line segment means given the probability of A, probability that A occurs, given that B has occurred, it's equal to the probability of A and B over the probability of the given, the second part. So that is a very useful formula, and they are both on your formula sheet. The probability of A given B is equal to the probability of both of those things, A and B, over the probability of B. We'll be looking at examples of this. Now, these two things are given to you. The two formulas for independence are not, to show whether or not they're independent. Independence means the occurrence of one is in no way associated with the change in the probability of the other one occurring. So if they're independent, the probability of A and B is just going to be equal to the probability of A times the probability of B. That's the way you can show whether or not events are independent, by multiplying them together and seeing if it equals the overlap between the two. And then the other way to show independence, that's one way. The other way, if they're independent, the probability of A given B is just equal to the probability of A. Okay, because it doesn't matter whether B occurs or not, the probability of A would stay the same. Okay, and once again, two events are independent if the occurrence of one event is in no way associated with a change in the probability of the other event. It's like flipping a coin and rolling a die and getting a 6. It doesn't matter what the flip of the coin was. Okay, the probability of rolling a die and getting a 6 is 1/6. All right, and then there's another concept, what is known as mutually exclusive or disjoint. Two events are disjoint. Or what is known as mutually exclusive. Mutually exclusive if the occurrence of one means the other could not occur, and the two events have no outcomes in common. In other words, like let's say if I say one event A is that you roll a 6-sided die and you roll a 1 or a 2. That's event A. And let's say event B is that you roll a 5 or a 6. Okay, they have no outcomes in common. If I told you B occurred, A could not have occurred. Now, let's say event C was that you roll an even number, a 2, 4, or 6. Now, there's overlap there with both of these events. So B and C are not disjoint. But A and B, if you made a Venn diagram, as we're fixing to do, A and B would look like this. They would be disjoint, a 1 and a 2, and then a 3 and a 4. but event C would overlap there. So that means disjoint. If one occurred, the other could not have occurred. All right, so let's look at some examples. Well, the first main sort of problem that you encounter in stats is a two-way table like this. And so let's see if we can solve these problems dealing with the two-way table. A random sample of citizens in a city were asked their opinion about the building of a new amphitheater in the city. They were asked if they approved of the amphitheater, disapproved of it, or didn't care. All right, they were also asked their age, and they were then categorized into these groups. So we have two variables, their age and their opinion about amphitheater. One of the things I wanted to say about this is that ordinarily you think of age as a quantitative variable, which wouldn't go in a two-way table. Well, any quantitative variable can be made into a categorical one by making categories like this, by assorting them in categories. And so this number right here, that's a count in a category. It's not quantitative. Okay, it's not like that some person was 70 years old, so to speak. Okay, that 70 means there's 70 values there. So this is a categorical situation. So whenever you have a two-way table, all right, so what you really need to do is to come up with the marginal distributions. And so we'll add up the total number that approved, that plus that plus that. And so that adds up to 106. Then we'll add up that plus that plus that. That adds up to 98. And we'll add up all of there. The total that don't care is 62. And then when you add up those three things, they add up to 266. That's the total number of people in the table. Then we'll add up the rows. And so this would be the row marginal distribution. And so we'll say 70 plus 30 plus 10, and that's 110. That's the total that are less than 30 years old. And then between 30 and 50, we say 24 plus 22 plus 18. That is 64 people. And then above 50 years old is 12 plus 46 plus 34, and that's 92. And when you add those up, that adds up to 266 as well. So now we're ready to answer some probability questions. So if you randomly select someone from the sample, find the probability they approve of the amphitheater. So well, how many approve of the amphitheater? 106. How many total possibilities there are? 266. And that's it. And that's considered showing your work, showing the fraction. Yeah, you don't have to put the decimal, but certainly you divide those two things and it's equal to 0.3985. So you certainly, you know, if you're looking for it in a multiple choice situation, that's what you would need to do. All right. If you were to randomly select one of these people, what's the probability they're above 50 years old and they disapprove? Well, above 50, that's these people, and they disapprove, that's 46. So that would be 46 out of the total of 266. And that in fact is equal to 0.1729. Okay. All right. Number 3, if you randomly select one of these people, what's the probability they approve given they are less than 30? All right, given. So when you have that's a conditional probability, the probability of one thing given another. So we can only look at what we're given. Given they're less than 30, well, that is these people. These are the people that are less than 30. So given we have one of these, we don't even look at the rest of the table because this is what we're given. We're given the people less than 30. Given they're less than 30, given it's one of these 110 people, what's the probability they approve? And so that would be 70. So it would be 70 out of 110. And so that is equal to 0.63 repeating. Like that. And once again, showing your work is showing the fraction. Make sure and show the fraction. What's the probability they disapprove if you know they are more than 50 years old? And that's another conditional statement. The probability one thing given another, in essence. So in other words, if you know they're 50, if you know it's one of these people, so we're just going to look at this row, just at these 90 people. What's the probability they disapprove? Well, there's 46 of them that disapprove. So you go 46 out of 92, and that is equal to 50%, 0.5. And then if you select one of these people, what's the probability they approve of the amphitheater or they're less than 30? Now, you could just, take, approve of the amphitheater be 106, and then add up those that are less than 30 that don't approve. That's one way to do it. But I want to use our little formula. Remember, the word or means add in math. And so the probability that they approve, and then or means, in essence, union, or that they are less than 30. That or means add. So that's the probability they approve plus the probability that they're less than 30. Okay. But whenever you add probabilities, you have to subtract off this, if there's any low overlap. Subtract off the probability of approve and they're less than 30. And that is our generalized addition rule right there. okay? And so, well, what's the probability that they approve of the amphitheater? Well, that would be 70. I'm sorry, that would not be 70. There's a total of 106 that approve. So that would be 106 out of 266, okay? And then plus, what's the probability that they're less than 30? Well, there's 110 of them. That'd be 110 out of 266. But we have to subtract off the overlap, approve and less than 30. That's 70. We counted these people twice. So we have to subtract them off once. Minus 70 out of 266. And so that would be, when you say that plus that minus that, so that plus that would be, 216, and then minus 70. And so that would be, yeah, minus 70 would be 146, I do believe. 146 out of 266. Okay. And showing those numbers right there, that's showing your work. It's showing the numbers. You don't have to show that little formula I did. You got to show your work. And so that ends up being, 0.5489. There we go. So that is how we do that. So, okay, on to page 2. If you randomly select 3 people in the sample, what's the probability they all disapprove? All right, so this is a multiple event, something happening 3 times. And for a multiple event in probability, you multiply. Multiple events means multiply. All right, and so multiply an event, they either have to be independent or you have to take into account their conditional nature. So if you randomly select 3 people, what's the probability they would disapprove? Well, if you select 1 person, what's the probability they'll disapprove? Well, there's 98 that disapproves, so it'd be 98 out of 266. So we will say 98 out of 266. All right, now, given that you've selected 1 person of the group and that they disapprove, what's the probability the second one is going to disapprove? Well, there's only 97 of them left that disapprove because you just took one of them out, and there's only 265 people left, okay, because you took someone out. All right, given that the first 2 disapprove, you've taken 2 people out that disapprove. There's only 96 of them left that disapprove, and there's only 264 left, and so you multiply those 3 things, and when you do that, you would get, according to my records, 0.04904, like that. And so that is how you handle that right there. All right, show whether or not being less than 30 and approving the amphitheater are independent. All right, so what we've got to do to show independence is we've got to use, in essence, one of our little formulas here. I'll choose that one. We have to show that when you multiply them together, it's equal to the overlap. So whether or not being less than 30, so if that's the case, the probability of less than 30 times the probability of approving is going to equal to the overlap, the probability of less than 30 and approving. Well, what's the probability they're going to be less than 30? So the probability that they are going to be less than 30 is 110 out of 266. So that would be 110 out of 266. What's the probability they're going to approve of the amphitheater? Well, there's 106 of them, so that'd be 106 out of 266. So that'd be 106 out of 266. And if they're independent, we multiply those 2 things, it should equal to the probability of both those things, less than 30 and approve. Well, less than 30 and approve is 70 out of 266. 70 out of 266. Well, when you multiply that left side there, when you say that times that, it ends up being 0.1648. And then 70 over 266, that in fact is equal to 0.2632. Those are not equal. And since they're not equal, therefore they are not independent. In other words, the occurrence of one would change the probability of the other one. And I would say that makes sense. And when you look at the table, if they're less than 30, they appear much more likely to approve. Whereas if they're greater than 30, it looks like they're more likely to disapprove or not care, right? So that's distinctly not independent. So 2-way tables, that's the first major kind of problem. The second major kind of problem is, in essence, a Venn diagram problem. So this says this. So this says 46% of 12th graders at a high school are in favor of having a dance contest at the prom. 52% of the 12th graders there are in favor of having competitive eating at the prom. 40% of the 12th graders there are in favor of both the dance contest and competitive eating. If you randomly select one of the 12th graders, find the probability that they, all right, whenever you're given the probability of one thing, the probability of the other, and the probability of both, all right, it's probably going to be the best thing that you do is to make a Venn diagram. And so this is what we'll do. And so we have two events here. They either want to have a dance contest, which is 46%. So I'll draw a circle. I'll put a D on that for dance contest. And that's 46%. So I'll put 0.46 in the upper part of the circle. And then it says 52% want to have competitive eating. So I'll make another circle for that. And so we know there's overlap, so I'll put overlap. And so we will call that C for competitive eating. And it says 52% want that. And then it says 40% want both. And so that says football shaped region, 0.4, like that. And now we can fill out the rest of the Venn diagram. If you subtract these two things, 0.46 minus 0.4, that's 0.06. That's this crescent shaped region. That represents people that want the dance contest, but not the competitive eating. And if I say 0.52 minus 0.4, well, that's 0.12. That represents the people that want the competitive eating, but not the dance contest. And then the outside of the Venn diagram are the people who want neither. And when you add up all four of these regions, this, and the outside has to add up to 1. Something has to happen. And so when you add up this plus this plus this, it adds up to 0.58. So that's the probability of the one or the other. Well, if you subtract that from 1, that's going to be 0.42. That is the probability they want neither. Okay, and we can use that Venn diagram. This would be considered showing your work for most all of these. So if you randomly select one of these people, what's the probability they're in favor of the dance or like competitive eating? Well, that would be that plus that plus that. Or you could do use the addition rule. Or means add. So we'll say, well, that's going to be the probability of dance. The dance contest, 0.46, plus the probability of competitive eating, which is 0.52. But you have to subtract off the overlap. We counted these people twice, minus 0.4. And that adds up. When you do that math there, it ends up being 0.58. There we go. Like that. What's the probability they're in favor of neither? They don't want neither one of them. Well, that's 1 minus the probability of either. So it's 1 minus 0.58, and that's 0.42. Right there. What's the probability they're in favor of the dance contest given they're in favor of competitive eating? All right, so once again, the probability of one thing given another on your formula sheet. A given B, one thing given another. It's the probability of both of them over the probability of the second one, over the probability of the given. So the little symbols for that, the probability they're in favor of the dance contest given they want competitive eating, it's probability of both of those things. Probability of dance contest and competitive eating over the probability of the second one, competitive eating. Well, the overlap, dance contest and eating, that's 0.4. And the probability of dance contest is 0.52. And so there you go. And so that would be 0.7692. I like that. Okay, what's the probability they're in favor of the dance contest, but not the competitive eating? Well, that means they're in the dance contest circle, but they're not in the competitive eating circle, and that's 0.06. Or you could say, well, in favor of the dance contest, that's 0.46, but you have to subtract off the people amongst that circle that are for the competitive eating. So it's minus 0.4, and so that's 0.06. Okay, there we go. And show whether or not they're independent. Okay, well, if they're independent, the probability of one times the probability of the other equals the probability of both, that and that. And so that would be 0.46 times 0.52. Is that equal to 0.4? Well, as it turns out, that times that, yeah, I believe is 0.7. No, it's definitely not 0.7. It's 0.23. It's 0.2392. That is not equal to 0.4. So therefore, they are not independent. They're not independent. Or the other way you could think of it, if they're independent, the probability of one given the other is just equal to the probability of the first thing. Okay, well, the probability of D given C, we found that to be 0.7692. And the probability of dance contest in general is 0.46. And they are not equal, therefore, they're not independent. So what that is basically saying is is that the probability they're going to want the dance contest is 0.46. But if I told you they wanted the competitive eating, the probability they want the dance contest goes up to 0.77, basically. Okay, so that's that. So thus, that completes that deal. Okay, so the next type of problem that we have, context 3. All right, 54% of students at a school are virtual students. If a student is virtual, the probability they have a job is 0.7. If they're not virtual, the probability they have a job is 0.2. Those are conditional probabilities that are given to you. They aren't asking for a conditional probability. They're given you. And when they give you a conditional probability, in other words, the probability one thing given another is true, or if another thing is true, all right, there's a good chance a tree diagram is the way to go. All right. And so what we'll say is this: 54% are virtual. So I'll express that as the first set of limbs for the tree. So I'll say V for virtual. So that's the probability they're virtual is 0.54. And so then virtual complement, that means virtual complement means not virtual. Okay. And so that's 1 minus that. And so that's 0.46. All right. And then it says if they're virtual, given you're at this part of the tree, the probability they have a job is 0.7. So that's 0.7. So what that means, given they're virtual, the probability they don't have a job complement is 1 minus that, which is 0.3. And then if they are not virtual, the probability they have a job is 0.2. So this would be 0.2. And then, so if they aren't virtual, the probability they don't have a job complement is 1 minus that, or 0.8. And so we have 4 events that you could be asked about with your tree diagram. So what's the probability that they are virtual and have a job? You multiply those two, 0.54 times 0.7, and so that is equal to 0.378. Okay, what's the probability going on this limb? The probability of virtual and they do not have a job, you would say 0.54 times 0.03, and that is equal to 0.162. What's the probability they are not virtual and they have a job? That's equal to 0.46 times 0.2, and that's 0.092. And then what's the probability they are not virtual and they do not have a job? And that's equal to 0.46 times 0.8, and that's equal to 0.368. Okay, and so those, you could be asked about any of those. You could be asked, given the stem of the problem here, what's the probability that they're virtual and they don't have a job? And you would do that. And you're showing the Venn diagram is in essence just showing your work. All right, if you randomly select someone from the school, what's the probability they'll have a job? Well, that occurs twice. It occurs there and there. So these people have a job and these people have a job. And so you would just simply say that's 0.378 plus 0.092, and that is equal to 0.47. Like that. So, so anyway, that's how, so that would be the probability of having a job. And then we have this is in essence a Bayes theorem problem. If you randomly select a student from the school, what's the probability they're a virtual student given they have a job? All right, that's a conditional statement. The probability that they're a virtual student given they have a job. Well, going back to our little formula again, that's the probability of both of those things, probability of virtual and job over the probability of the second one, job. Virtual and job, that's 0.378. Found that up there. And the probability of job, we just found that number 13, so that's 0.47. And you divide those things and you get 0.80426. There you go. And so that's how you do that. All right, and so now from that, and so that's a tree diagram problem. So that's the third big. We got, you got two-way table problems, you got Venn diagram problems, you got tree diagram problems you got to know how to do. So then we're going to go to the next thing, which is what is known as binomial problems. Binomial problems is when you have a set probability, a set number of trials, and then they ask you about a number of successes. So in this one says, if you randomly select 5 students from the school, what's the probability that exactly 3 of them will be virtual? So that would be our probability of success in this problem, our P is 0.54. And it's giving us N a sample size in essence, and X a number of successes. And when it gives you a P, an N, and an X, that is what is known as a binomial problem. Okay, binomial problem. You have a fixed number of trials. And so if the probability of success is 0.54, if you have 5 trials, what's the probability of 3 successes? And so let me show you how to do that with your calculator, first of all, and then I'm going to show you the little formula in the formula sheet. So this is what is known as a binomial PDF problem. And so binomial PDF it's with the other PDFs and CDFs. It's in the distribution menu. And so you can just go second vars, which is distribution, scroll all the way down to binomial PDF. PDF for 1 point, CDF for cumulative. So PDF is this one. Our number of trials is 5. Our probability success is 0.54. And then X, our number of successes is 3, right like that. Okay, some calculators will immediately take you to this screen and you just put, 5, 0.54, 3 like that and hit enter and there's your answer. That's it. So 0.333319. So that would be 0.33319. That's it. Now, the little formula, which you have to be able to identify the formula. You can always use your calculator. You have to be able to identify this formula on your formula sheet. And that is down here on the first page. If it has a binomial distribution, that is, in essence, the formula you got to be able to identify. And there's your mean and standard deviation, which will come in handy in a minute. But let me plug the numbers into this. So this is n over x, p to the x, and then 1 minus p to the n minus x. And so this is going to be what we call 5 choose 3, be the first of it. Our probability success is 0.54. And we have 3 successes. Well, if we have 5 trials and 3 successes, that means we get 2 failures. And our probability of failure is going to be 1 minus that, or 0.46 to the second power. And if you were to find that, it's equal to that. So, and using your calculator, by the way, to find that, you could use binomial PDF, but let me just show you how you would find this using your calculator if you wanted to. So this is 5 choose 3, and you can get that on your calculator by going to the math button. So if you hit math and go to probability, so it's that function right there, the third one, and you hit enter and just enter 5 and 3, 5 and then 3 and hit enter. And so it's 10 and then just go times 0.54 to the third power, enter, and then times 0.46 squared. Boom, and there's your answer. So that's how you would, in essence, do it by hand. Now, if you randomly select 5 students from the school, what's the probability that at most 2 of them will be virtual? All right, so let's think about this. Let's think about our possible number of successes. If we have 5 trials, if you look at 5 students, how many of them could possibly be virtual? Well, it could be 0, could be 1, could be 2, could be 3, could be 4, could be 5. Those are the total possibilities for your number of successes. What's the probability of at most 2? At most 2 means it has to be 0, 1, or 2. So what you could do is you could do exactly what you did in number 15, except do it 3 times. Do it with x is equal to 0, x is equal to 1, or x is equal to 2. Or you could use what is known as binomial CDF. CDF is the cumulative function. It tells you the probability of a certain value or below it. So what you can do is you can go binomial CDF, and you put it in alphabetical order. Our n is equal to 5, our p is equal to 0.54, and then our x is less than or equal to 2. And so this is what you would enter. So you would go second vars, which is distribution, and scroll down to binomial CDF for cumulative. So CDF for cumulative, our number of trials is 5, our probability of success is 0.54, and our number of successes is, since it's cumulative, that's going to be 2 or below. And it's like that. So it's 0.4253. So that would be, 0.4253, like that. And that would be showing your work. Now, by the way, showing your work on this last one, you could show that formula, or you could write binomial PDF. So binomial PDF like this, and write the letters. Don't forget, don't just write the numbers. You have to write the letters. And so in this case, n is equal to 5, p is equal to 0.54, and then x is equal to 3. If you wrote that, you get full credit for showing your work, or you could show the formula. So please make sure and do that. All right. So then it asks, all right, if you randomly select 5 students, what are the mean and standard deviation for the number of virtual? Binomial situation, that's your mean, that's your standard deviation. Your mean is n times p, your standard deviation is that, and don't round it to the nearest integer, by the way. So our mean is equal to n times p, and so our n is 5, and our p is 0.54, and when you multiply that, you get 2.7. That's if we did repeated sampling, that is our average number of virtual kids, the number of successes, so to speak, in here. Our sigma is equal to the square root of n times p times 1 minus b. So that's going to be 5 times 0.54 times 0.46. And when you do that, you would get 1.11445. There you go. And so that's how you find the mean and standard deviation of a binomial situation. So you have to identify a binomial situation. That's going to take practice to identify these binomial problems. Just remember, whenever you're given a p, an n, and an x, in other words, a probability of success, a number of trials, and a number of successes, that's binomial. Okay. And then we have this, a geometric. Geometric is when it asks for, when is your first success? If you were to randomly select students, what's the probability your first encounter one that virtual is the fourth one? Well, if your first success is the fourth one, what that means is you had to have had 3 failures. If your first success is your fourth one, 3 failures and then 1 success on the 4th trial, 1 success. What's the probability of 3 failures in this situation? Our probability of success is 0.54. So the probability of failure is 0.46. And the probability of that happening 3 times would be to the 3rd power. Then you finally have a success. One of them, 0.54 to the 1st power. And you just simply multiply that and you would get 0.052561. Boom. That is what we call a geometric. This is a geometric problem. That's really the main geometric problem we have. There's that's in essence that little formula. To me, it's better to just intuitively think it out. There's the little geometric formula. The mean, by the way, is 1 over p, and there's the standard deviation. So that's if they ask you the mean of a geometric situation, just go 1 over p. So you go 1 over 0.54. So if it asks you for the mean, which it didn't, but let's just pretend it did, 1 divided by 0.54, and so the mean would be 1.85. So there you go. So there we go. All right, now let's talk about discrete random variables. A table like this, a probability distribution. All right, the number of people living in the apartments of a complex vary from 1 to 4 with the proportions of each expressed in the discrete random variable below. So in every apartment either has 1, 2, 3, or 4 people living in it. And so the probability distribution, this is basically saying 10% have 1 person, 20% have 2 people, 24% have 3 people, and 46% have 4 people. Now, first of all, obviously these probabilities have to add up to 1. So if they didn't give you one of them, which happens, you can just say 1 minus the rest of these to find that. Okay, if you randomly, and it could ask you a simple question, what's the probability that there's more than 2? Well, if the probability of more than 2 means it's got to be 3 and 4, and so you'd add those and you'd say, well, that'd be 70%. If you randomly select one of these apartments that have more than 2 people. But then let's say if it gives you this, if you randomly select an apartment in the complex, what's the probability that has at least 3 given that it has more than 1? All right, let's think about that. The probability that has at least 3 greater than or equal to 3 given, that real line segment means given, all right, that has more than 1, x is greater than 1, okay? Well, let's use our little formula that is on our little formula sheet. The probability of one thing given another. It's the probability of both of those things over the probability of the second one. So that would be the probability of x is greater than or equal to 3 and x is greater than 1 over the probability of the second thing, the probability that x is greater than 1. But think about this. What's the easier way of saying that something's greater than or equal to 3 and it's greater than 1? Well, if it's greater than or equal to 3, it's obviously got to be greater than 1. So the easier way to say this is the probability that x is greater than or equal to 3, that numerator, and then the bottom stays the same. So in problems of this type, it's just, it's with conditional, it's just going to be the probability of that over that. And so that, in fact, what's the probability that it's greater than or equal to 3? Well, greater than or equal to 3 is that plus that. And so that's 0.7. All right, what's the probability it's going to be greater than 1? Well, greater than 1 means it's going to be 2, 3, or 4, and those add up to 0.9. And that divided by that, that's going to be 0.7 repeating. There we go. So that's how you do that. And then what are the mean and standard deviation of this random variable? All right, so we have a little formula there. So our little formula for a discrete random variable is that the mean, otherwise known as the expected value, is the sum of every x times every p. And then the standard deviation is this. It's the square root of the sum of every x minus the mean squared times its probability. You know, we're going to use our calculator for this, but if you're doing this by hand, it's not hard. It's a bit tedious. So the first thing to find the mean, you just say that times that. You know, so you say that times that, and that's equal to 0.1. So and that times that, that's equal to 0.4. And that times that's equal to whatever it is. Okay. And what the heck, we'll do it the hard way. We'll do it using the formula. And so we would say 3 times 0.24. And so that's equal to 0.72. And then we would say 4 times 0.46. And that's equal to 1.84, like that. And then add them all up. And so the mean mu is the sum of all those. And so we'll just say 0.1 plus 0.4 plus 0.72 plus 1.84, and that's equal to 3.06. So that's equal to 3.06. That would be the mean, okay? And and that seems reasonable because when you look at the average of these numbers, 4 is occurring 46 of the time. So, so that's going to pull the mean up toward it. So anyway, the standard deviation, we could use the formula for that. I'm just going to use my calculator. The standard deviation is not hard, it's tedious. You would just say 1 minus 3.06 squared times 0.1, 2 minus 3.06 squared times 0.2, and do it for all of them and then add them up and take the square root. But this is how you use your calculator for this. And so I'm going to put these in lists. So I hit stat and edit. So let me clear out these lists. And in list 1, I'm going to put my x values, 1, 2, 3, and 4, my number of people. So that's 1, 2, 3, 4, like that. And then in list 2, I'm going to put the probabilities for each. And so that would be 0.1 and 0.2 and 0.24 and 0.46. Like that. And then all you've got to do to find the mean and standard deviation is one variable stats. So you go stat, calculate one variable stats. My X list, this is list 1. Now these, my frequency list is these numbers, these probabilities. So they're in list 2. That's how we go second list 2. This is the only time all year we put anything in the frequency list, aside from 1 or 0. So remember to change it back after you get done with the problem. So I go like that, boom. And so there's my mean, X bar, and there's my standard deviation. It's also the only time of the year we'll use that sigma on the calculator. So therefore, sigma, the standard deviation, it's like 1.02781. There you go. That's how you find the mean and standard deviation of a discrete random variable. Okay, we're getting there. And so let's see. Context 5. All right, the times the workers at a factory spend in training each month vary uniformly. There's the key word, not normally. It's uniformly, okay? From 0 to 6 hours. If we randomly select a worker, find the probability they spend more than 4 hours in training. Uniformly means it's going straight across, it's a rectangle. And so I like to just figure out these uniform problems, just draw a rectangle. And it says going from 0 to 6, so 0 to 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Here's all the times that the workers spend in trading. What's the probability to spend more than 4 hours? The way I think of these problems is this. Now, technically, to be a true density curve, the area of this rectangle has to be 1. And so the height of this would be 1/6. But to make these calculations, I just like to go ahead and say the height of this rectangle is 1 and use the areas in the rectangle to work this. And so the area of this rectangle is 6. So, 6 times 1. All right. What's the probability is more than 4 hours? So more than 4 hours. So this right here. And so it's the area of the, if you were to randomly select one of these points in this rectangle, what's the probability in the shaded, you'd be in the shaded region. And so you'd say, well, the shaded area, it is 2 by 1. So it's 2 over the area of the whole rectangle. It'd be 2/6, which is 0.3 repeating. That's it. And so that's it. So it's just the shaded area over the area of the whole thing. All right. What's the probability more than 4 hours given that it's more than 2? All right. Given that it's more than 2. So we go like this. Given that it's over here, okay, if you were to randomly select a point in there, what's the probability to be in the shaded region? Well, the shaded region here, once again, the probability to be greater than 4 is 2 over the probability of the given, which is 1, 2, 3, 4, 2/4, which is 0.5. That's the way I reason out the uniform problems. It's just all about rectangle areas. All right, and then we have combining random variables, which is one of the more missed sort of problems in the world of AP stats. So this one says the amount of money that Farmer Bob makes from selling his potatoes each month varies approximately normally. Aha, approximately normally. Maybe we'll be using our friend normal CDF. With that mean and that standard deviation, mean of 600, standard deviation of 20. The amount of money that Bob makes from selling his turnips varies approximately normally with a mean of 500, standard deviation of 40. If you randomly select a month, what's the probability he'll make a total of at least $1,200? Okay, so let's write this down. So his potatoes vary approximately normally with a mean of 600 and a standard deviation of 20. The amount he earns each month from his turnips also varies approximately normally, and the mean is 500 and the standard deviation is 40. Okay, and by the way, one of the things I left off, darn it, was the fact that we've got to assume that these things are independent, okay, in order to do these problems. So otherwise the formula, we can't combine their standard deviations. So independent, assume they're independent. So anyway, all right, so what's the probability of the total? All right, so what we in essence need is we need the distribution for the total. The total is P plus T. And when you add together two normal curves, you also get a normal curve. You can add their means. The mean is 1100, okay? So this notation means normal, that mean, that's standard deviation, okay? But the trick is this, you cannot add the standard deviations, you have to add the variances. The variance is the square of the standard deviation. So the variance of the potato is 20 squared, which is 400. The variance of the turnips is 40 squared, and that's 1600. So when you combine P plus T, the variance of potato plus turnip is 400 plus 1600, that's 2000. And so therefore, the standard deviation of potato plus turnip is the square root of 2000. And I'll just leave it like that. And so this would be the square root of 2000. That is the little trick. And so then you can just say, what's the probability the total will be more than 1200? And so you'd say normal CDF more than 1200. That'd be 1200 to infinity. Our mean is 1100 and our standard deviation is root 2000. So let me remind you in your calculator. Now to show your work for normal CDF, remember you got to label this as lower bound, upper bound, mu, and sigma. And so here we go. And so we'll go second distribution, normal CDF, and we will go 1200 to infinity, or you could just put 9 billion or whatever, that's fine. And then 1100, and then the square root of 2000. And so boom, and there's the answer, 0.01267. So that would be 0.01267. In other words, it's pretty unlikely to occur. So there we go. All right. Next sort of problem. If you randomly select a month, what's the probability he makes more money from turnips than potatoes? And so whenever it asks you, you got two normal curves, what's the probability that you're going to select one from here and it's going to be more than the one from here? Okay, more greater than or less than, you're going to subtract the two. And so more money from turnips than potatoes. And so I'm going to subtract them in that order. I'm going to say turnips minus potatoes. When you subtract two normal curves, it also generates a normal curve. That means you can just subtract 500 minus 600. And so it would be negative 100. But, and this is a bit counterintuitive, but it's true. When you subtract two normal curves, you still add the variances. You're combining the variabilities of the two curves. And so it's still going to be 400 plus 1600, and then take the square root. It's like the Pythagorean theorem. You know, you're going to square these things, add them, and take the square root. And you do the same thing even when you're subtracting 2000. And so then you say, all right, what's the probability they make more money from turnips than potatoes? Well, if they make more money from turnips than potatoes, turnips minus potatoes would be positive if T is more than B. And so we do normal CDF with the positive numbers. Normal CDF, 0 to infinity. Our mean is negative 100. our standard deviation is root 2000. And let's label those LB for lower bound, UB for upper bound, mu and sigma. And when you do that, let's see what we get. There's a bit of a coincidence that happens here. So second distribution, normal CDF, we go 0 to infinity, and we would say negative 100, and that's the same thing there. And it ends up being the exact same answer as the one above it, coincidentally, because I happened to pick, in essence, a difference of 100 in both of them. So it's just a coincidence there. And then the last problem, if you randomly select 3 months, what's the probability that Bob will make at least $2,000 from potatoes? So now we aren't worrying about the turnips, just the potatoes, which, so the potatoes vary for 1 month, very normally with a mean of $600, standard deviation 20. So what about 3 months? So what about 3 months? Okay. All right. You would expect that it's pretty intuitive with the mean. Well, if 1 month is averaging 600, for 3 months, you just multiply that by 3, it's averaging 1,800, and that works. But you cannot do that with the standard deviation. You can't multiply and say that's times 3. It would be a different thing that if we took 1 month and multiplied it by 3. Then, like we've done earlier in the year, you just multiply those things by 3, and you would get 1,860. But you're getting 3 different months now. You're not 1 month, and there's a difference between getting 1 month and multiplying it by 3 and getting 3 different months. Okay, and so if that's the case, you have to multiply the variance by 3. The variance of P is equal to that squared, which is 400. And so the variance of 3P is equal to 3 times 400, and that is 1,200, like that. And so our standard deviation would be the square root of 1,200. So what's the probability that curve is at least 2,000? And so you would say normal CDF, at least 2,000, so that would be 2,000 to infinity. Our mean is 1,800, and our standard deviation is root 1,200. So that is our lower bound, that is our upper bound, that is our mu, that is our sigma. Let's see what we get. And so we would go second distribution, normal CDF, 2,000 to infinity, and then 1,800, and then the square root of 1,200, like that. Boom, look at that number, 3.89 times 10 to the negative 9th. So that would be approximately equal to 3.894 times 10 to the negative 9th. In other words, 0.0 with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. 3.894. In other words, basically 0. It's extremely unlikely to happen. And the thing about it is root 1,200. Let's see what that is. The square root of 1,200, it's like 34. Well, these things are, 200 apart from each other. So that's like 6 standard deviations or something like that, which is incredibly, that's a lot. And that's a lot of material, and that's it. That's probability for you. That's a quick run through of all the major areas of probability. It takes practice, get good at it. So do some practice, work in your Barron's book. And if you got any questions, please send them to me. Thanks for watching.